Bismillah ar-Rahman ar-Rahim. This is lecture 7 on Ampere's circuital law. Recall that in electrostatics, the sources of the electric field were related to the field by Gauss's law, which is the integration over a closed surface of d dot ds equal to the charge enclosed, which by using the divergence theorem gives the point form or the differential equation governing the field, which is divergence of D equal to the charge density rho v. So the flux density D is directly related to the charge by this equation, and it is independent of the medium. In magnetostatics, we saw that from Ørsted's experiment that the circulation integral of the magnetic force per unit magnetic pole, which was B, or the force per unit current moment, is newtons per ampere meter, was related to the current as the line integral around the closed path of B dot dl equal to mu naught I, which upon using Stokes' theorem becomes the differential equation governing the field, which is the curl of B equal to mu naught times the current density J. We introduce another vector that is independent of the medium and directly related to the current I, which is defined by Ampere's law. The line integral of H dot dl around the closed path C is equal to the current enclosed I, which upon using Stokes' theorem is the curl of H equal to J. So H is related to B by the relationship B equal to mu naught times H. H is designated as a magnetic intensity field. It is called the magnetic field intensity because it's given by the line integral. And this is similar to E, which was the line integral of E dot dl equal to VAB, which is the potential difference between points A and B, which gave us the curl of E equal to 0. So let us summarize Maxwell's equations for electrostatics and magnetostatics up to this point. It is the curl of E equal to 0, and in integral form it is the line integral of E dot dl around the closed path C equal to 0, the curl of H equal to J, which is Ampere's law, which is the line integral of H dot dl equal to the current enclosed I, and divergence D equal to rho v, which in integral form is Gauss's law, D dot ds around the closed surface equal to Q, the charge enclosed, and the divergence of B equal to 0, because the lines of the magnetic field or magnetic flux are closed lines, so we get 0. Now we come to applications of Ampere's law. For symmetrical problems, Ampere's law provides an easy way to calculate the magnetic field intensity H. So if we take an example of the infinite straight wire, which is perpendicular to the page in the direction of plus Z, the first step is to identify a closed Amperian path, an Amperian path of integration, which satisfies two requirements. One, that H is always tangent to the path, as in here, and two, that H is constant along the path. So for the infinite straight wire along the z-axis, a circle of radius rho centered on the wire satisfies these requirements. Thus the integration of H dot dl around the circle, H here is tangent to the path and it is in the direction of dl, so H is constant, it factors out of the integral, and the integration is just the length of the path, which is 2 pi rho. Thus we get 2 pi rho Hy equals to the current enclosed, so H is I over 2 pi rho in the direction of A phi. Another example is the magnetic field of an coaxial cable. The coaxial cable is made up of an inner cylindrical conductor of radius A and an outer cylindrical shell, conducting cylindrical shell of inner radius B and outer radius C. The inner conductor carries the current plus I along plus Z, and the outer conductor carries current minus I along minus Z. The circuit is assumed to be closed at plus or minus infinity, so we can look at this problem in two different ways depending on whether the current is DC or high frequency AC microwave. It could also be low frequency AC, which is the case of power cables. Now, for the case of DC or low frequency AC, the current is distributed as a volume current density with Ji equal to the total current divided by the cross-sectional area. So it is a uniform current density here in the inner conductor, and in the outer conductor it is minus I divided by the area of the cross-section, which is the difference between the two areas of the circle of radius C and the circle of radius V. Okay. In the very high frequency case, the current is distributed as a surface current as a result of the phenomenon of skin effect, which you will study in the next course, 307. So here we will have a surface current on rho equal to A, let's call it Ka, in amperes per meter. So it's equal to the total current I divided by the perimeter, 2 pi A. It's in the direction of AZ. And we have the current density on the inner surface of the outer conductor. It's on the inner surface because of the attraction of the two. In electrostatics, you had this, for example, plus rho S, and here it will be minus rho SB, here rho SA, and here rho SB. But here, it is the current, charge in motion. So it is minus I divided by the perimeter 2 pi B, rho equals B. Now we can apply Ampere's law. For the case of the DC cable, the Amperian path is any circle of radius rho as for the infinite straight wire, so that the line integral of h phi around the path gives this, and the current inside, the current enclosed, is just integration of j dot ds. So for rho less than or equal to a, j is ji, so that h phi is I times rho divided by 2a squared inside the inner conductor. It's linear in rho. And for rho greater than a but rho less than b between the two conductors, the only current enclosed is the inner current, total current I. So again, we get h phi equal to I over 2 pi rho as if we had the total current on the axis, just like the straight wire. Okay. And for B less than rho less than C, the total current enclosed in Ampere's law is the inner current I minus the portion of the outer current enclosed by the circle of radius rho between B and C. Okay. So if we combine, we find h phi is equal to this, and if rho is equal to C, this becomes 0. So outside the coaxial cable, we have no field, h phi equals 0, just as we had for the electrostatic case. The electric field was 0 outside the cable. Now, for the case of high-frequency cables, microwaves, for rho less than a, I enclosed equals 0 because there is no current inside. The current is on the surface. So h phi equals 0 inside. It will be 0 here. And then it will jump to I over 2 pi rho between A and B, and for rho greater than or equal to B, the current enclosed is 0, so H phi will be 0. Now, if we look at the figure of the variation of H with distance, with rho, for the case of DC cable, it is linear inside, decays as 1 over rho outside between A and B, and then decays non-linearly to C, to 0 at C. But for the high frequency cable, it is 0 inside up to A, and it jumps to this value and then continues until we reach B and drops down to 0 between B and C, and for rho greater than C.